Hey, welcome to episode 3, the final episode for the DragonBone Quantum, an electronic dice roller that uses noise from the quantum vacuum to seed its random number generator. In this episode, we're going to look at the source code. Stay tuned. Alright, so let's go ahead and take a look at the source code. The top section kind of explains what this source code is, talks about the quantum vacuum, etc. You'll notice that there are some libraries that are included, such as the file system. I'm using LittleFS. We're using the ESP8266 Wi-Fi for the connection. We set up a DNS server for the soft access point. I'm using Wi-Fi Manager. It's a great library. It makes getting all the information about the SID and the password for the local Wi-Fi much easier. We are using the quantum cache. We are using the ESP true random quantum. These are actually local because I have modified them. I did not want to fork the source code for the ESP true random. I just went ahead and took it and modified the local copy, which will be uploaded with this source code. So the ESP true random code is being used, and I'll show you how that works. Mostly used for the analog pin. So if you don't have any quantum seeds, then it will use the analog pin. Let me explain that a little bit. So A0 on the ESP8266, the D1 Mini, I've left open. And the theory is if you set that pen to a read mode and then you go to read it, you will get random noise on the pen. I have found that the randomness of the pen is extremely limited, but it is somewhat random. So with that, let's continue on. This is the long click timing in milliseconds. So all of these are set up so that you can change the behavior. This is the LED display timer, how long to keep an LED lit. So if it's not staying lit long enough for you, you can change this value. I set it for 2 seconds. This is the soft access point timeout. So when you turn the device on, if it doesn't have Wi-Fi already set up, it sets up a soft access point so you can connect to it. I'll show one of the screens here. We've covered it in episode 1, I believe. And this is how long it waits before it just shuts down and says he's not gonna, this person's not going to log into the soft access point, in which case it goes back to using the analog pin for its noise, for its random number generation. Pulse width max range. This is used for really the snoring, and this is the snoring range. And let's see, inactivity before it starts snoring is 10 seconds. These are the pens that we're going to use on the board and what they're for. These map to the schematic basically. This is the number of dice we have, and it is as simple as putting in, let's say, 50 comma right here, and you will get a 50-sided dice. Super easy. You don't have to do anything else. You put 50 there, 55, 60, you get those dice. So that's super easy. We got a button class we're using here. We've got a state machine that I'm using that I wrote. And these are the states that the device can be in. So as you'll see, there's a loop. And in that loop, we look at what state we're in, and that determines where we are in the process of doing whatever it is we're doing. The current state is a power on display. Obviously, we just powered on. This is the default state. And then in terms of some of the activity, I need to track certain types of things with the Wi-Fi, if it's been connected, if it's disabled, as well as the file system. So that's what those are for. We create a Wi-Fi manager. We create an app key. This is some of the information it presents to you so that you can enter your own ANU quantum API key. And I'll show you that. I don't think we've actually gone to the site, and I know that I've shown you the text, but you can go and get a free account. So that's really all there is to it. Really no reason to show it. You can go get yourself a free account. They give you an API key, and when you turn on the device and you go to the soft access point, that's where you enter your API key. So you can get quantum keys. There's a limit to how many you can get per month. Again, the software takes care of everything. If for some reason you run out of quantum keys, then it starts using the noise on the analog pin. This is information about your passwords. If you want an access point password, you can put it right here. If you just want to leave it open, you can do that as well. Let's see. Then we have the quantum cache. This is the 512 numbers, and that represents this class right here, the quantum cache. This is the struct for the quantum cache. Currently, it gets 512 quantum numbers of size unsigned int, 16-bit int. And let's see. This is the threshold. If there's only X number left, that's when we need to go and get more. Right now it's just set to 0. You could set it to 5, and when it gets to 5 left, it goes out and gets them. It's up to you. Here's an inline piece of code that determines whether we need to load the quantum cache or not, and it looks at the quantum cache struct and determines, when we need to load the keys and how many are left. Excuse me, this is the setup. We have a debug value so that if you want, you can actually look at the output. You just plug it into your USB like any other, like an Arduino or whatever, and you can actually get on the serial monitor all of these outputs. So you can do some debugging. Excuse me, this is all the pin values, things about the level shifter, how we talk to it, buttons that we're setting up here. So all of this is what happens in the very beginning. Then you have certain set of functions. So this is what's called first, if you're not aware. Then it starts to loop. These functions here aren't called until they're needed. So let's take a look here. Load app settings file. So this is load app settings file. So what this one does is it loads the settings that it has stored in Flash so that it can reconnect to your Wi-Fi. This is how you save them. It uses, again, that little file system class. Load the quantum cache. This is how the quantum cache gets loaded from disk because it saves them. So it goes out, gets 512. Maybe it uses 50 of them, and it remembers on the file system on Flash how many it's used, where it's at in the number set. It can save it. This is the show on, power on, show off. It just runs some lights. You can change that if you want, runs them up and down, I think. This is how you activate the Wi-Fi, and this goes through the process of trying to activate the Wi-Fi. Creating the portal name is here. You can change that if you want, I don't care. Saving the config, the callback to save the configuration for the Wi-Fi manager class. Okay, and then here's the heart of what we're doing. This is the main loop. So in the main loop, this is called multiple times. That's why there's a state machine. So we are calling this thing over and over and over again. So as you walk through it, you'll see where it's, checking, are we using Wi-Fi? Are we not using Wi-Fi? Was Wi-Fi disabled or not? So this is all the logic that goes into trying to figure out what's going on. And for battery saving, if you have Wi-Fi on, it only needs to turn the Wi-Fi on. If you've already set up the SID and the password for your home Wi-Fi, it only needs to wake up when it needs to get seeds. So it's smart, and it shuts itself down for power saving. So all of that logic is already here. This is the time delta, like how much time since the last event. In this case, like clicks. And so what it's looking at is, are we snoring? Are we waiting? It's looking at each of those states to determine what we need to be doing. In this case, this is the code that figures out if we're snoring or not. So this is the heart really of the state machine. Either we're snoring, We're doing power on display, which is the default first call. We're doing a device reset. You press both buttons and hold. We're doing an LED on countdown, meaning I just displayed something to you, and we're using that 2 seconds, which you can change. We're using that 2 seconds to determine when to turn it off. This is to determine what we're doing next. Long press for select dice. We want to display to you what you had previously selected. So the long presses, if you remember, let's say you've chosen a 20-sided dice, a long press on the select will show you that you chose a 20-sided. A short press will select the next one up from 20, which would be 30 in the default state. Same with the roll. You press quickly the roll, and you're going to get a random number generated. If you press and hold it, you're going to see the last random number that you generated. If you press and hold both for a while, you'll create a reset of all of the Wi-Fi data so that it'll create a soft access point again, and then you can provide new information to it. So that's really what all of this is about, is state management. Then we have some stuff down below that's managing the serial parallel, those 74LS595s. This is how basically we're pushing bits through. This is how, okay, so I told you we had to do some math to figure out what buttons, and I'll show the bit value that I showed on the previous video here. So what you're doing is basically doing a mod 10, trying to figure out where we are with these numbers. Where in the tens are we, if we're in the tens, and then where in the 1 through 9s are we? And that's exactly what this does. It builds a bit pattern which represents the LED positions in the bits so that it can be pushed out. And you can see where it's basically doing that. It's pushing 17 to 24, byte 9 through 16, and 1 through 8. Basically pushes those out through the 595s and then turns it on so that you can see the number. And then goes into a state where it's trying to determine how long to show you that number. And then there's some shift out code. I actually think the shift out code might have come from the Arduino site, I think. There was some article about using the 595 serial or parallel shift registers, and I think I just copied it. This is how we load the quantum cache. This talks about the API for the quantum numbers, and it kind of explains the format in case you need to see it. Here it builds it up. This is the quantum key right here. I'm wondering if you could probably hard code yours in there if you want, but it is supposed to go and read it. So before we go too far, do we even have an API key for the quantum seeds? And it looks at the API settings.api key. So it should be reading the API key value from those settings. I mean, if not, you can fix it. This is open source. It kind of goes through, again, it's doing some debug, so you can plug this in and see exactly what's going on. Goes out to the site, it parses all the values. Here's a sample of some of the data it sends. And so you'll see that there's a parser here using like string toke, I believe, and yeah, string toke. And so I parse it out and load it into the cache, and you're ready to go. This is the release handler and the click handler. And the long press handler. That's all there is to this code. It is not rocket science. It sounds complicated. It's not really. The most complicated thing about writing this probably was just figuring out what states were needed, how to set the states up, and how to pass information between states. So you know the LED is on, the LED is off, it's in the timer state, that kind of stuff. Okay, so something I really wanted to show you was what happens when you press the roll button on the device. So if we look at the roll dice state, the roll underscore dice state, you'll see that what it does is it determines what is the max range. If the user has selected 20 or 100 or a 12-sided dice, it needs to know what that max is. The minimum's always 1. Then it calls the ESP true random the random range. So this actually is where I've modified the ESP true random class into a new class called ESP true random quantum. And if we look at that, random range is really the the core of what this is going to do. So it determines, are we using quantum keys? And if we are, it takes care of all the calculations. It grabs the next quantum seed, puts it into the random seed call, and generates the random number. If we don't have any seeds available, then it basically steps down to using the analog pen, and you can see that in this section of code right here. So that's really all there is to it. Quantum seeds, you go out, you get them, you load them into the cache, and then the ESP true quantum or ESP true random quantum class takes care of what it's going to use, getting the next one, and processes all that. So then basically it calls display random number, which goes through, calculates what the byte pattern is, the bit pattern actually, for that on the LEDs, and it displays it, turns it on, and basically goes into an LED on countdown call, which is how long we're going to show that before we turn it off. That's all there is to it. So anyway, this is all available. The link should be down below to the Bitbucket site, where you can get everything for this project. You can get the case, you can get the Fusion 360, and you can change them all if you want. You got the source code, you got the schematic. In the schematic, there's even a zip of the Gerber files, so you don't have to mess with it if you don't want to. I'm making this open source, and you can run with it. I am not going to continue doing much with the project. It's available for people to play with in a non-commercial manner. I don't expect you guys to try to sell this. This is for everyone to play with. All right. So that's pretty much it for this project. I hope you've enjoyed it and learn something new every day. I'll see you next time for the next project. Thanks.